Good day, everyone. This is Dr. Mansour Al-Matarni from the University of Jordan. This is the second lecture about the Schrödinger equation. Again, we need to solve Schrödinger equation. H operates over a psi in terms of coordinate to produce or to form the total energy A, and gives us the wave function back again, R and R with respect to both electron and the nuclear code. So to solve this independent Schrödinger equation, to define the psi. So let's start with the Hamiltonian. So let's talk about one-dimensional coordinates. So that's one-dimensional, and this is in a classical mechanics. So if we write in terms of momentum, where P equal mv, right? And here, if we rearrange and make B square, that will equal P square over m square. Now the Hamiltonian again, and if you write it, the energy in terms of momentum, you will end up with P square. Again, just substitute the V square here. You end up with P square over 2m plus Vx, the potential in terms or in x-axis. And this energy really represents the Hamiltonian, right? And that's represent the Hamiltonian, because any quantum mechanics, the momentum, right? Momentum is an operator. So the momentum, actually, the quantum mechanics, h bar over I, the first derivative with respect to x in terms of one-dimensional coordinate. So the P square equal, because I multiply I square, which equal minus, so we end up with minus h bar square d second derivative with respect to x square, so that the P square. So simply the Hamiltonian will be minus h bar square d square dx square. So the Schrödinger equation then, the Hamiltonian over psi in terms of r will equal minus h bar square over 2m second derivative with dx square. This is multiplied by psi, of course, plus, let's see, plus b x, and this multiplied by psi in terms of r, right? So this is basically the Hamiltonian, right? So that's the Hamiltonian in a quantum. We need to define the Hamiltonian by defining and determining the kinetic and potential energy for the system in general. Again, what about psi now? What about this value? The assumption here will be a product form for a function. Psi in terms of electronic coordinate and nuclear coordinate will equal psi e, the electronic wave function with respect to electronic coordinate, times psi, or nuclear wave function in terms of nuclear coordinate r. And that's really what we called Hartree product. So we need to separate the variable here. So simply, this is the electronic wave function, and this is the nuclear wave function. If we substitute this equation into the Schrödinger equation. So in terms of electronic coordinate plus the H in terms of a nuclear coordinate. So again, we separate the variable in terms of Hamiltonian as well. And this Hamiltonian acts over the psi electronic wave function in terms of R multiplied by psi n in terms of R. And again, this equal what? Here we multiply the electronic Hamiltonian in the first term and also in the second term. So we end up with these two terms. So the electronic Hamiltonian multiplied by psi e, psi n, plus psi e multiplied by hn psi n. So, and this is equal, of course, the energy, the total energy multiplied by psi er psi n r. Right? Again, if you look at this term, this is very interesting thing because this one resists separation are held fixed. So the nuclear coordinates are considered parameter in this case. And this is really argument here that there's no differentiation or integration is performed for the parameter. So parameters are held fixed, and not like the variables, because variables do vary, right? So now if we divide this equation by psi e psi n, right, we end up with this equation. So we have, again, if we divide this, so 1 psi e multiplied by electronic Hamiltonian multiplied by psi e plus 1 over psi n, and that's Hamiltonian, and psi n. And this is equal, of course, the last term here. If we divide this term here, we'll end up with only the energy. Again, the Hamiltonian, the electric Hamiltonian, apply for psi e and psi n as these parameters are held fixed. But in the last term, the Hamiltonian, this Hamiltonian operate over the hn operates over psi n. Okay, this term represent the electronic energy in terms of R coordinate, and the second term represent the nuclear energy. Okay. So simply we can separate these two equations into two equations. The first one will be the electronic Hamiltonian with respect to R over or acts over the electronic wave function psi e r equal E electronic energy with respect to R and psi r. So that's the first equation, and that's what we call electronic Schrödinger equation, the first one, electronic Schrödinger equation. The second one, we have the nuclear Hamiltonian with respect to R operates over a nuclear wave function with respect to R, and this is equal to En, the nuclear energy, and psi n with respect to R. And here we have to talk about the Born-Oppenheimer approximation, because it breaks the original problem into two problems that must be solved, really. The first one, which is the electronic structure, nuclei held constant, and the second one where we deal with the nuclear dynamic, nuclear dynamics, simply where we introduce the potential energy surface. What is the Born-Oppenheimer approximation? Hamiltonian can be written in 5 terms. The electronic, again, the electronic Hamiltonian plus the nuclear Hamiltonian. According to von Oppenheimer, now this term is equal 0. Why? Because the nucleus is really massive. It's almost like 1848 times heavier than the electron. So the kinetic energy of a nuclei or nucleus equals 0. And this term, the last one, the nuclei repulsion forces, this one held constant. And this is really, can be easily calculated by the classical, Coulomb potential. And this term, it will be added later to the total energy. So the Hamiltonian now will be really equal the only these 3 terms, which is simply represent the electronic Hamiltonian. So will be 2e plus the V and E plus V E E. These only 3 terms according to von Oppenheimer. So the total energy will be the electronic energy, the one we talked about in the last slide or whiteboard. So the total energy will be the electronic one plus the V and N. So this term will be added at the end of calculation because it can be easy calculated. So the total will be these 2 terms. So that's for the Hamiltonian according to the von Oppenheimer approximation. Again, von Oppenheimer is the approximate separation of variables. All right, now let's take one example about the Hamiltonian, how we write Hamiltonian for the for H2 molecule, right? So the example here will be write the Hamiltonian for H2 molecule, for H2, right? So again, we have 2 nuclei. So we have here A, for example, and we have B, 2 hydrogen atoms, and we have electron example or 1, 2. Right, so here we have repulsion, which is 1, 2. Here we have 1A forces, that's R 2B, and here we have repulsion between R A B. Also there here 2A, so another attractive forces between 1B, right? So again, to write the Hamiltonian for the H2 for H2 molecule, we have 5 terms to represent the system, right? Now, because we have a summation, so we need really to split this term into 10 terms, right? So again, because we have the total Hamiltonian will be energy for electron 1 plus the kinetic energy for the second electron, and also we'll have what? We'll have the kinetic energy for A, for nucleus A, and also kinetic energy for nucleus B. So we have 4 kinetic energy values here. Plus, what about the potential here? We have the potential, we have the V 1A, plus we have V 2A, plus we have V 1B, plus we have the we have 2B, plus we have the V 1, 2 between the electron, and also we have the V AB. So again, how many terms now? We have 1, 2, 3, 4, 5, 6 potentials, and also 4 kinetics. So again, this is just like, make it really easy to understand how we deal with this, right? So again, the Hamiltonian now will equal, according, to the general expression for the Hamiltonian, will be the kinetic. If you remember this, using, the atomic unit, will be minus half del 1 square. For the second one will be minus also half del 2 square, 2m like a with del square a minus 2m b, and that will be del square b. So these the kinetic energy for electrons and the nuclei. All right. Now minus the ZA. Now the potential between electrons and nuclei. What we have? ZA over R1A minus ZA R2A minus ZB divided by R1B minus ZB over R2B plus 1 over R1, 2. This is the potential between electron 1 and 2, and also plus the ZA ZB divided by RAB. Okay, that's it for this lecture. Thank you for listening and have a good day. Bye-bye.